Hello everyone, I am Tarunuba, a final year student at IIT Guwahati, and I would be giving a presentation on the topic Randomized MST. Let's move through the contents. First, I'll be introducing to what is MST, followed by deterministic algos for the same. Then we will look into Borufka's algorithm, which is key to our random algorithm. And finally, we will be touching on all the details for helping us understand the random MST algorithm, ending it with the proof of how the algo has a linear expected time complexity. So let's directly head into the contents. Introduction to minimum spanning tree. Let's familiarize ourselves with notation GV, E, which represents connected graph with real valued edge weights. So what is a spanning tree? A spanning tree in G is an acyclic graph of G that includes every vertex of G and is connected. Every spanning tree has exactly n-1 edges. The weight of a tree is the sum of the weights of its edges. The minimum spanning tree is the spanning tree of minimum weight sum. Now you would be wondering its importance. Now let us give an example. Now consider a telecommunication company trying to lay cable in a new neighborhood. If it is constrained to buy the cable along certain paths, that is, they have to bury only on the certain paths that have been specified, then there would be a graph containing the points connected by those paths. Some of the paths might be more expensive because they are longer or you have to dig deeper into the ground. These paths would be represented by edges with larger weights. A spanning tree for that graph would be a subset of those paths that has no cycles but still connects every house. There might be several spanning trees possible, but a minimum spanning tree would be the one with the lowest total cost, representing the least expensive path for laying the cable. The reason behind this example is that the first algorithm for MST, that is Borovka, came in light in 1926 to solve the same problem. This algo is used widely in day-to-day basis and hence piqued my interest to dig deeper. Now let's talk about minimum spanning forest. Let GV, B be a disconnected graph. A spanning forest F is a forest whose trees are spanning trees for the connected components of the graph G. A minimum spanning forest F, which is represented by V, E0, is a subgraph of GV, E such that the sum of all the weights WE for all the edges of E in E0 is minimal. Consider the diagram here. We can see that the diagram on the right hand side contains many different disconnected components, right? Now let's see, this is the first component up here, this is the second component we can see, and this is the third component. Each of these components can be shown to have a tree, a minimum spanning tree for each. For example, in the first we have this and so on. Combination of all these edges will form a E0 for all the vertices V. Combining all these minimum spanning trees for each disconnected component and summing it up, we will get a minimum spanning forest. We can assume for the purpose of this presentation that the weight of the edges of G are all distinct. This can be ensured by indexing in case of equal weights, and it would guarantee that only one MST exists for each graph. Only the ordering of weights is important for all algorithms, and the actual value of weights do not really matter. Moving on, let's read about the deterministic algorithms for MSTP. Here are a few. First of all is Kruskal algorithm. It is a greedy algorithm in graph theory, as in each step it adds the next lowest weight edge that will not form a cycle to the minimum spanning forest. Second one is Prim's algorithm, which operates by building this tree one vertex at a time. From an arbitrary starting vertex, at each step are adding the cheapest possible connection from the tree to another vertex. And finally, we have Boruvka's algorithm, which will be coming up in detail. Let's talk about our main algorithm. The basic idea is to contract simultaneously the minimum weight edges incident on each of the vertices in G to give G dash. Let the set of contracted edges be T. Now, how is this contraction happening? Retain only the minimum weight edge out of any set of multiple edges, and also remember to eliminate the self loops. Recur the algorithm to find MST of G dash, and then finally sum up all the edges and return MST of G dash union T. Now, let us go through all the phases of Boruvka. First of all, mark the edges to be contracted in G and store them in a separate step T. Determine the connected components formed by the marked edges. Replace each connected component by a single vertex. And finally, eliminate the self loops and multiple edges created by these contractions. And at the end, return the contracted graph G dash. This will be more clear with an example. So let's consider this example. Initially, MST is empty. Every vertex is a single component as highlighted in blue color in below diagram. For every component, find the cheapest edge that connects it to some other component. Now, in the diagram, we can see that for 0, we have 0 to 1, which is of minimum weight as compared to all other edges. So we have green colored. Similarly, for 1, it is same, so we will not double count it. Set is unique, so only unique edges will be going in it. Then we move on to 2, where we have 2 to 8. And similarly, the cheapest edges are highlighted in green as shown. And now we can see that in figure number 4, all the connected edges, connected vertices, sorry, all the connected vertices can be shown here. These are the final connected components after our phase. 0 and 1 share the edges, so they will be treated as one vertex in the graph G dash. Similarly, 2, 3, 4, 8 here are connected and they will be also treated as a separate vertex. In short, after one single phase, we have brought down the total number of vertices of the graph from 8 to 3. We again run the same conditions and we will get the similar vertices. Taking the union of all the vertices, we will continue till we have only one vertex left. After taking all the unions, we get our final MST, where we can see 0 to 1, which was in our first step, first phase, 1 to 2, which was in second phase, and so on. And this would have given you a very clear picture of how this algorithm is working. Now let's infer or talk about some lemmas that we can understand from Borovka's phase contraction. Lemma number 1. MST for G must contain the edge V, W, that is the minimum weight edge incident on V. This lemma we can prove as in this first step only. We are only choosing those edges which have the minimum weight edge incident on V, and hence this lemma is true. We can also prove it by contradiction, that let MST not contain the minimum weight edge of V. Add the minimum weight edge to MST to form a cycle. Remove another edge with more weight from cycle MST dash. As we can see, MST dash is less than MST, which is a contradiction. Moving on to our next lemma 2. The set of edges marked for contraction during a Borovka phase induces a forest in G. This we can prove by lemma 1. Each selected edge is an edge of the MST that we have been putting in our set T. The set forms a subgraph of forest and may not be connected but are acyclic. Moving on to our next lemmas. Lemma 3 states that graph G1, G dash has at most n by 2 vertices and m edges. Number of marked edges is at least n by 2. Why? As an edge can be minimum weight for at most 2 vertices, and each marked edge must eliminate a distinct vertex, because we are only taking into consideration those edges that have not been visited at a time and are from different connected components. So at a single moment, we will be removing at least a vertex. Each contacted edge can be the minimum incident edge on at most 2 vertices. The number of marked edges is thus at least n by 2. Since each vertex chooses exactly one edge to mark, it is easy to verify that each marked edge must eliminate a distinct vertex. As I said, lemma 4. The MST of G is the union of the edges marked for contraction during this phase with the edges in the MST of G dash. What does that mean? This means that we have to at the end take the final union of all the edges that we are saving in the sets. The marked edges are part of MST of G by lemma 1. G dash also covers vertices of G itself, and for S of G dash, union marked edges would cover all vertices of G with no cycle. Moving on, we have on our hand the pseudocode. Now, pseudocode is really essential because we might be asked to, at some point of life implement it. So let's give you a brief intro to what type of code we will be writing. Input will be a connected, weighted, and indirected graph. Could be an adjacency list. Initialize all vertices as individual components or sets. Initialize MST as empty first of all. While there are more than one components, do following for each component. Find the closest weight edge that connects this component to any other component. That is, look into its edges, adjacent edges. And when you find the minimum, add this closest edge to MST if not already added. Then get the final components from the G, put it in G dash, and then recursively compute the minimum spanning tree for G dash. At the end, we will be returning the union of all the edges in set T as well in T dash. Now we will be analyzing the time complexity of Borovka phase. which we will say that it is of m plus n. How are we going to prove it? Marking the edges is takes of m plus n, cause we will be looking out all the edges. Second, to find connected components and assign them a vertex, we can use DFS. As simple as that. As DFS from any of them which is not visited, we will be moving through them, and then we will assign them a vertex that is a parent. And third of all, handling loops and the multiple edges, which will take O of m. After doing the second phase, third phase will be very easy, and hence it will be taking just O of m. Time complexity for the algorithm will be T of n comma n, which will be less than T of n by 2 comma n, as n by 2 vertices will be remaining, plus O of m plus n from the 3 phase. Leads to T of n comma n is equals to O of m log n. This concludes that Borufka algorithm takes time of O of m log n, and the Borufka phase takes only O of m plus n, which will be very useful because we will be using Borufka phase in our randomized algorithm. Let's head into getting knowledge about what we will be using in our final algorithm. First, we will talk about heavy edge and MST verification. Now, if f is any forest of G, then weight of u comma v will be the weight of the edge u comma v in G, and weight of u comma v with respect to f, that we will be talking like wf of u comma v will be the maximum weight of any edge along the unique path in f from u to v. If the path does not exist, then wf u comma v will be infinity. An edge u comma v, which is an element of E, is said to be f heavy if weight u comma v is greater than weight of f u comma v and f light otherwise. The terms are self-explanatory. In particular, all the edges in f must be f light, and edge u comma v is f heavy if the forest f contains a path from u to v using only edges of weight smaller than that of u comma v itself. Now we will take into consideration lemma 5, which says let f be any forest in graph G. If an edge u comma v is f heavy, then it does not lie in the MST of G. The converse is not true. Now, this is a very important part. This will be useful in removing unwanted edges when we'll be taking into consideration our algorithm. Now, you have been given a forest in graph G. Now, let u comma v be part of the MST. Let's consider it. As u comma v is f heavy, then there exists a path from u to v with smaller weights. Now replace this in the MST to get MST dash. Now MST dash is less than MST, which is a contradiction as MST in itself is minimum spanning tree. Hence, we took into consideration that the F will only have F heavy in no way. Yeah. F may contain isolated vertices say u. Now we will be proving that the converse is not true. Weight f of u comma v will be infinite because u is an isolated vertex and u comma v is f light, but it will not be in the MST. Thus converse is not true because there is no backing into the MST to that edge. In short, we can say that if we are given a forest and it is isolated, then how can we infer that that edge will be in the MST, right? There's nothing to back that proof that it could lie in the MST, and hence it is not true. Now, how to verify if a given forest T is the MST? A verification algorithm for the MST can be viewed as taking an input, a tree T in a graph G, and checking that the only T light edges are the edges in T itself. This is equivalent to verifying that T is the MST. Now, given a graph G and a forest F, all F and V edges in G can be identified in time of n plus m using Kagos algorithm, which we will not be discussing in this presentation. But this is a very important thing. Remember that in O of n plus m, we can identify all the heavy edges in G. Now, we will be talking about random sampling for graph. So, the randomization comes in identifying and eliminating edges that are guaranteed to not be in the MST. That is our basis of the algorithm. GP, the graph contained from G by selecting each edge with probability P, where P is greater than 0. It has n vertices and MP expected number of edges. For reasonably large P greater than 0, we expect the minimum forest of GP to be close to the MST of G. The lemma 6 says that the number of F-light edges in G is stochastically dominated by a random variable x that has the negative binomial distribution with parameters n and p. In particular, the expected number of F-light edges in G is at most n comma p. Now, let us create a basis for proving this lemma 6. We need a little more concept for our probability distribution. A random variable x has the negative binomial distribution with parameters n and p if it counts the number of trials required to have n success, where each trial has a probability of success p. That's like a coin toss. We want to find out in the probability when we have n heads. As you can see, the random variable x has the negative binomial distribution with parameters n and p, and here are the given probability function in expected time. Expected time of the same is n by p. Lemma 7 says that let x have the negative binomial distribution with parameters n1 and p, and y have the negative binomial distribution with parameters n2 and p. For n1 greater than n2, x stochastically dominates y. That is, for all z is an element of R, probability of x greater than z is greater than or equal to probability of y greater than z. The process is pretty simple. Probability of x greater than z can be represented as 1 minus probability of x less than equal to z, which can be written as probability of 1 minus probability of x equal to z is equal to z minus 1, then x is equals to n1. Similarly, for probability of y. Now, taking into consideration that n1 is greater than n2, we can infer the probability of x equal to z till x is equal to n1 is less than equal to probability of y equal to z till probability of y equal to n2. And therefore, we can prove that probability of x greater than z is greater than equal to probability of y greater than z. So let's prove our lemma 6. Expected number of F-light edges. Initially F is empty. At step I, after the coin is flipped, for the edge EI equal to U comma V, if EI is chosen for graph P, where P is the probability of selecting an edge, When AI is considered for inclusion in F, the edge is added to F if and only if U and V belong to different connected parts of F till what we have seen. Like, as we are considering the edges, then we are putting into the edges that we are getting as chosen, we are making the forest. If it is not connected, then we will put it in. Total number of F-light edges processed till the end of phase S is distributed as the sum of S independent geometrically distributed random variables, each with parameter p. Account for the F-light edges processed after that but not chosen for GB, we continue flipping coins until a total of n heads have appeared. The total number of coin flips is a random variable which has the negative binomial distribution with parameters n and p. S is at most n minus 1. It follows that the total number of F-light edges is stochastically dominated by the random variable which represents the total number of coin flips as shown in lemma number 7. The expected number of F-light edges is bounded from above by the expectation of this random variable which is np, and hence lemma 6 is proved. It is the expected number of F-light edges is np. Now we have created our base. We have seen the algorithm we will be using. We have done the time complexities for the same. We have seen the lemmas that will be monitoring or guiding our algorithm. Now let's join all this together to create the final algo. Now input is a weighted undirected graph of G, V, V with vertices N and M edges. And output would be a minimum spanning forest step for G. The first step would be using three applications of Provoca phases interleaved with simplification of the contacted graph. We will compute a graph G1 which will have at most n by 8 vertices. Why n by 8? Because of Provoca. 1 by 2 is reduced each time. So n by 8 vertices at the end of 3 phases. And let C be the set of edges contacted during the 3 phases. If G is empty, then exit and return F equal to C. If G2 is equals to G1, P be a randomly sampled subgraph of G1. Now we will be doing the random sampling that we just learned about, where P is equals to half. And then recursively apply algorithm MST, compute the minimum spanning forest F2 of the graph G2. Now we have got a forest for the graph G2. Now using a linear time verification algorithm, identify the F2 heavy edges in G1 and delete them to obtain a graph G3. We will recursively apply algorithm MST, compute the minimum spanning forest F3 of the graph G3, and finally return forest F equal to C union F3. Now this would be a bit more complicated when we are reading, but when you picturize it, what we are doing is first of all, apply Brovika phases, get a smaller graph, randomly sample a graph so that we have a subgraph, apply MST to compute a forest for G2. After applying it, we will be removing edges from G1 to get a smaller graph G3 and continue the process and then return the forest F. As simple as that. Not as simple as I am saying, but it is simple to understand now after we have gone through all the cycles of. Finally, the analysis for expected time complexity. Let Tm, n be the time complexity of the algorithm MST for a graph with n vertices and m edges. Following is the time taken at each step. Time for 3 invocations of Provoca faces. G1 is equals to at most n by 8 percentage MHS, so O of m plus 1 into 3, which is also O of m plus 1. Random sampling to give G2 is equals to G1 half, that is O of m plus n. Right? Because G2 is equals to expected vertices of n by 8 vertices and m by 2 edges. Because we are random sampling, so expected edges would be m by 2. Recursively using algorithm for MST of G2, there will be time of n by 8 comma m by 2, followed by step 4, which will be a linear time verification algorithm to give G3, which will be O of m plus n. G3 will have at most n by 8 vertices and n by 4 edges, as we have learned from lemma 6, which we have proved also. Recursively using algorithm for MST of G3 will be Tn by 8 comma n by 4, and at the end we will be taking union of F3 and C, which will take off n. Now sum it up. So what we have on our tree is T of n by 8 comma m by 2, which was in our second step. As for third step, as far as in the third step we have Tn by 8 comma m by 2. All the other steps are taking O of n plus m or O of n, which can be summed up as C of n plus m, and the T of n by 8 comma n by 4, which we are taking from the fifth step. So we have our equation, the final equation. Now the solution 2Cn plus m satisfies the above equation. Now first of all, let the base n is equals to 1 and m equal to 0. T1 comma 0 is rho of m. Now consider the hypothesis that T of n by 8 comma m by 2 is less than 2Cn by 8 plus m by 2, and T of n by 8 comma m by 4 is less than 2Cn by 8 plus m by 4. Using the induction, we can prove that T of n comma m is less than 2Cn plus m. Thus, we have an expected linear time randomized algorithm for MST of a weighted undirected graph. And that is the end of this presentation. Thanks for being here. I hope you enjoyed it. Thank you and have a nice day.